Hello everyone, I'm Jay Lee from UNIST EAI Lab. Today I would like to present about my research. The title is Designing Extremely Memory Efficient CNNs for On-Device Vision Tasks. Following research has been done with my colleague Yoel Park and with my advisor Sergey Lee. And this paper has been accepted at ACCV 2024 and has awarded as Best Application Award. And these are the contents for today's presentation: introduction, related works, proposed network, and implementation, experiment results, and conclusion. So let's begin from introduction. So what have we done? We have developed a memory-efficient AI model specifically optimized for microcontroller units, short for MCU. This model is designed to operate entirely within the kilobyte memory range, making it highly suitable for devices with severe resource constraints. It will be applicable on drones, surveillance camera, IoT devices, etc. Our AI model is capable of performing tasks such as image classification and object detection. Despite its compact size, our model delivers performance comparable to state-of-the-art CNN models like MobileNet V2 and MCUnets. It addresses the memory and storage limitation of MCUs, making it ideal for edge AI applications where efficiency is crucial. Now, related works. Regarding related works, I will briefly explain MobileNet V2, which serves as the backbone structure of our network. One of the key characteristics of MobileNet V2 is its use of sequenced inverted residual bottleneck structures. As shown in Figure 2, the bottleneck structure operates as follows. First, expansion layer. It starts with 1x1 convolution layer that expands the number of channels. Second, depthwise convolution. The expanded output passes through 3x3 depthwise convolution layer, processing each channel independently. At this stage, peak memory usage occurs as the input, kernel, and output must be stored during computation. Third, projection layer. It is last 1x1 convolution layer that projects the output back to reduced number of channels. This bottleneck structure is widely adopted in various CNN models, including ours. Now, I will introduce the details of our network. So, our proposed network. To provide a brief overview of our network's contributions, we have made three key contributions: input segmentation, patch tunneling, and bottleneck reordering. First, with input segmentation, we divided the input into 5 segments. These segments are not divided uniformly, but instead have overlapping regions, specifically 4 overlapping parts, along with additional central segment, making a total of 5 segments. Next, while MobileNet V2 passes through only one single branch of model, on the other hand, since our input has been segmented, the separated inputs will go through a sequenced bottleneck branches all the way until the end, which we named as patch tunneling. And for the bottleneck reordering, we have modified the order of CNN calculation, which I will explain in more detail at next slides. So starting from 1x1 convolution from bottleneck reordering, in original MobileNet V2 bottleneck, all of the kernels are computed with whole input, which result in multiple output channels. But instead, at our bottleneck reordering method, it will compute only one single kernels of a 1x1 convolution and save to the pre-allocated memory. After computing the first 1x1 kernel, the output with one channel will compute 3x3 convolution in the state of single channel. And the second 1x1 kernel will be computed and saved at second channel of allocated output. And so on, the last kernel will be computed. Also, we want to emphasize that memory will require only one single channel of output instead of whole channels, which will save the memory significantly. Now the depthwise 3x3 convolution. At MobileNet's bottleneck depthwise convolution, whole input channels will be computed with whole kernel, which will result n number of channels. But at our reordering method, depthwise 3x3 works differently. We just compute single channel from output of previous 1x1 convolution and compute only single kernel from 3x3 kernels, which will result single channel output. By using this method, the memory that requires will reduce significantly because at the standard depthwise convolution, whole inputs and outputs should be stored. But in our case, only single channels of input, output, kernels will be stored in memory, which, in conclusion, if we set input channels as n, we can save the memory about 1 over n times. And the second channel input will be computed with second kernel and gives us the result of second channel output. And the last input will be computed. At this stage again, it is important to note that only single channel have been computed and only single channel will be passed to next convolution, which is 1x1 convolution. Now, the last stage of bottleneck reordering. Normally, as we can see at figure 12, whole input computes with all of the 3 1x1 kernels that result in 3 channels of output in this case. On the other hand, in reordering method as colored, only single channel, which is output of previously computed reordered 3x3 depthwise convolution, are computed with corresponding channel from the kernel and gives us a result of multiple channels. And as the stage goes by, the results will be accumulated, which I have pointed out as plus equal. And the second layer will be computed and output will be added with previously computed first channel of output. And the last layer will be computed. So we're saving memory by computing only single channel instead of multiple channels, but gives us exactly the same result. So to sum up, we have 3 contributions, which are segmenting the input data, patch tunneling, and bottleneck reordering, which made to save the peak memory and preserve the performance. And now the implementation. We have embedded at STM32H7 board. It has a flash memory of internal flash of 2 MB and 2 external flash memory of 64 MB. SDRAM is 32 MB and SRAM is 1 MB. And it has 2 cores which are dual, M4 and M7. Now the experiment result. We have done classification and object detection tasks with our network. Classification. From now on, I will discuss the results of our experiments. These experiments were conducted using our network MCUNet V1, MCUNet V2, and MobileNet V2 on the ImageNet dataset, which is classification task with 1000 classes. We observed that peak memory usage of 63 KB is the lowest among all current networks. Additionally, it achieves an accuracy of 61.58%, which is comparable to other models and demonstrates competitive performance. Next, I will present the results using Visual Wake Word dataset, which is another ImageNet classification dataset with 2 classes, person and not person. In our experiment with quantization, our model achieved an accuracy of 82.63% at a memory usage of just 18 KB. While MCUNet V2 achieved state-of-the-art performance with an accuracy of 90% at peak memory usage of 30 KB. Our result of 18 KB demonstrates a significant and meaningful achievement. Now, let me explain the results about object detection. For object detection task, we have made experiment in using Pascal VOC and MS COCO dataset, and these results are by using Pascal VOC. And as it can be seen, our network has the lowest peak memory, which is 65 KB, with comparable MAP score. Now let's discuss object detection results using the MS-COCO dataset. For MobileNet V2, the peak memory usage is 10,080 kilobyte, achieving a MAP score of 31.8%. In contrast, our network demonstrates a significant improvement in memory efficiency with a peak memory usage of just 112 kilobyte and MAP score of 21.2%. Additionally, it achieves an MAP score of 30% with peak memory usage of only 1,719 kilobyte, which is approximately 1/6 of MobileNet V2's peak memory's requirement. And now, conclusion. So, in conclusion, we have made a network that is memory efficient, minimum of 60 kilobyte of peak memory, and with ImageNet dataset reaching up to 61.58% of accuracy. We have achieved low memory usage while maintaining strong performance, comparable to state-of-the-art CNN model, which is MCUNet. In designing the network, we have three main contributions, which are input segmentation, patch tunneling, and bottleneck reordering. We have done vision tasks such as classification using ImageNet and VWW dataset, and object detection task with Pascal VOC and MS-COCO dataset. We have embedded one of our models in STM32H7 board successfully. Thank you so much for listening to my presentation.